Dear students, we are going to discuss some more numericals based on electrostatic potential and potential energy. The first question is like this. A regular hexagon of side 10 cm has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. So this is that regular hexagon A, B, C, D, E, F. At each vertices, a charge of 5 microcoulomb is placed. For a regular hexagon, the distance of each vertices from the center of the hexagon is equal to the side length of the hexagon. So what's the meaning of that? Distance of each vertices from center of the hexagon means AO is equal to BO is equal to CO is equal to DO is equal to EO as well as is equal to FO, and that will be equal to side of the hexagon, and the side of the hexagon is given 10 centimeter. 10 centimeter in SI unit, it will be 0.1 meter. We have to find out the potential at this point due to the charges present here. Each charge is 5 microcoulomb and each distance is same. Therefore, the potentials due to these charges remain same at this point. So altogether 6 charges produces potential here. So total potential at center O is equal to 6 times potential due to a single charge. So the potential due to a single charge will be 1 by 4 pi epsilon 0 q divided by L, and if you are substituting the data 6 into 9 into 10 to the power 9, charge q is 5 into 10 raised to minus 6 and length L is 0.1 meter, and that will be 2.7 into 10 to the power 6 volt. So that will be the result of this particular question. Let us discuss another question. The question you can read: 3 point charges plus q plus 2q minus 3q are placed at the vertices of an equilateral triangle of side L. If these charges are displaced to the midpoint A dash, A1, B1 and C1 respectively, find the amount of work done in shifting these charges to the new locations. So initially the charges are at A, B and C. Charge at A is Q, charge at B is 2Q and charge at C is minus 3Q. So initial potential energy we can calculate. Initial potential energy is the amount of work done to assemble these system of charges, and we already studied potential energy is equal to potential energies of each pair. Total potential energy or initial potential energy is equal to potential energies of each pair. So the first pair I am taking this Q and 2Q, and the distance between them is L. Therefore the potential energy will be 1 by 4 pi epsilon 0 Q into 2Q divided by L, plus second pair 2Q and minus 3Q. Distance between them also will be L. Therefore 1 by 4 pi epsilon 0 2Q into minus 3Q divided by L, and the third pair Q and minus 3Q. Therefore that potential energy will be 1 by 4 pi epsilon 0 Q into minus 3Q divided by L. Now 1 by 4 pi epsilon 0 can be taken out. Then it will be 2Q square by L minus 6Q square by L minus 3 into 1 minus 3Q square by L, and that remains in the bracket. So it will be minus 6 minus 3 minus 9 plus 2, it will be minus 7Q square by L. So the total potential energy, initial potential energy U1 is equal to minus 7 by 4 pi epsilon 0 into Q square by L. Put it as equation number 1. Now they are asking to find the new potential energy when the charges are shifted to the position A1, to the position B1 as well as to the position C1. So that means the position of charge Q is now at A1 and position of charge 2Q at B is now at B1, and position of charge minus 3Q at C is now at C1. So the distance between the charges reduces to L by 2. You can see The symmetry help us to find out that the distance between the charges is not L right now. The distance between the charges is reduced to L by 2. So we have to find out the final potential energy corresponds to this orientation. So potential energy final is equal to potential energies of each pair. The first pair is Q and minus 3Q. So you can see here the first pair is Q and minus 3Q I am taking. So it will be 1 by 4 pi epsilon 0 Q into minus 3Q divided by L by 2. The distance between the charge is L by 2 right now. Plus 1 by 4 pi epsilon 0 Q into 2Q divided by L by 2. The second pair is Q and 2Q. The distance between them is L by 2. And the third pair is 2Q and minus 3Q. The distance between them is also L by 2. Therefore, it will be 1 by 4 pi epsilon 0 2Q into minus 3Q divided by L by 2. Now you can see this L by 2 goes to the numerator, therefore it will be 2 by L. So that will be common everywhere. So 1 by 4 pi epsilon 0 into 2 by L can be taken out. And what remains in the bracket is minus 3Q square plus 2Q square minus 6Q square. So that will be minus 7Q square. So altogether 1 by 4 pi epsilon 0 2 by L into minus 7Q square. That means potential energy final is equal to minus 14 divided by 4 pi epsilon 0 Q square by L. Put as equation number 2. So we got initial potential energy, we got a final potential energy. So we already studied work done is equal to change in potential energy. Work done is equal to change in potential energy. So therefore it will be final potential energy minus initial potential energy. So it will be minus 14 divided by 4 pi epsilon 0 Q square by L minus of the minus that will be plus 7 by 4 pi epsilon 0 Q square by L. So the final result will be W is equal to minus 7 by 4 pi epsilon 0 Q square by L. So this much work is needed in order to shift the charges from the original position to new position. The work done by the external agents comes out to be negative. Actually this work is done by the electrostatic field only. No work is needed in order to do that automatically under attraction. Since one charge is negative, under attraction this work is done by the electrostatic field only due to attraction of the charges. Now let us discuss one more numerical. So here it is the question. Three concentric metallic shells A, B and C of radii small a, small b and small c, small a lesser than small b lesser than small c, have the surface charge densities sigma, minus sigma and sigma respectively. If shell A and C are at the same potential, obtain the relation between the radii A, B and C. So very carefully understand the situation. So we have three concentric spheres, metallic spheres or conducting spheres. This is the inner sphere A that has a radius small a. This is the middle sphere B that has the radius small b, and this is the outer sphere C that has the radius small c. And the charge density is given by sigma. Inner sphere, middle sphere it is minus sigma, and outer sphere it is sigma again. Now we already studied what is the potential due to a spherical conductor. Potential on the surface of a spherical conductor is given by V is equal to 1 by 4 pi epsilon 0 Q divided by capital R, where Q is the charge given and capital R is the radius of the surface. Now here charge density is given. So I am going to substitute the Q in terms of charge density. We already studied the charge given Q is equal to surface charge density into 4 pi r square. So if I am substituting this equation here, I will be getting potential due to a sphere 1 by 4 pi epsilon 0 into sigma 4 pi r square divided by capital R, 4 pi r square divided by small r, or it will be capital R, I think. Yeah, it is capital R. So this is the potential due to the charged conducting sphere on the surface. So 4 pi cancels. So what remains is 1 r also cancels. What remains is V is equal to sigma r divided by epsilon 0. So what is sigma? Sigma is the charge density. What is r? Radius of the sphere. What is epsilon 0? Absolute permittivity of free space. Now let us analyze the situation very carefully. One thing is given, potential at A is equal to potential at C. The total potential at the surface of A, VA, is equal to total potential at the surface of C, VC. Now what is potential at A? Potential at A is the sum of two things. Potential due to its own charge density plus potential due to charge densities on B and C. Why it is like that? This is the inner surface A. It has its own charge density sigma that creates a potential according to this equation. According to this equation we already studied, and this inner sphere resides inside the spheres C and B. So inside the sphere C and B, the potential remains same as that of the surface potential of C and B. So on the surface of the inner sphere A, B also create a potential and C also create a potential, and these potentials created by B and C will be equal to potential of the on the surface of B and the potential on the surface of C, because inside a spherical conductor potential remains same as that of the surface. So here three potentials are there on the surface of A. Now what is the potential due to its own charges? Sigma into radius divided by epsilon 0. What is the radius of the inner sphere? Small a. So it will be sigma into small a divided by epsilon 0. So this is the potential due to its own charge minus potential due to charge density on B. What is the surface charge density on B? Minus sigma. Therefore potential due to B will be minus sigma into radius of B divided by epsilon 0 plus potential due to C, sigma into radius C divided by epsilon 0, because radius of the outer sphere C is equal to small c. So on the surface of the inner sphere, potential is there due to its own charge, that is sigma a by epsilon 0, and inner sphere is residing inside a potential that is created by the charge density on the second sphere as well as outer sphere. So altogether potential VA can be written as sigma by epsilon 0 can be taken out, and A minus A plus sigma C by epsilon 0. So put it as equation number 1. Now we are going to discuss what is the potential on the outer sphere VC. Potential on the outer sphere can be written as potential due to its own charge density plus potential at C due to charge densities on A and B. So listen please, this is the C, it creates its own potential, and you can see B also has certain charge density. So outside the surface of B, the B creates a potential. Similarly outside the surface of A creates a potential. Therefore in addition to the potential of C, its own charge density, B also create a potential here, A also create a potential here. Now we are going to analyze potential at any point outside the sphere. What is the potential at any point outside the sphere? V can be written as 1 by 4 pi epsilon 0 charge on the sphere divided by distance from the center to that point. This is not a radius. If it is radius, it is the potential due to potential on the surface only. This is at any point outside the sphere. Now what is Q? Q is sigma into 4 pi r square. Therefore potential can be written as V is equal to 1 by 4 pi epsilon 0 into sigma into 4 pi r square divided by r. 4 pi cancels. What remains is sigma r square divided by epsilon 0 r. So this equation is different from this equation. This equation gives potential at any point on the surface of the sphere. This equation gives potential at any point outside the sphere. What is sigma? Surface charge density on the surface of the sphere. What is r? Radius of the sphere. And what is small r? distance of the point under consideration from the center of the sphere. Now very carefully listen. We see can be written as sigma c by epsilon 0. What is sigma c by epsilon 0? Potential due to its own charge given by this particular equation, sigma into radius c by epsilon 0 minus potential on the surface of C created by charge density minus sigma on the surface of B. According to this equation, that will be minus sigma into radius of B. That will be B square, radius of B square. Okay, divided by epsilon 0 into what is R? R will be this is the center of the B, and we are considering the point on the surface of the C, therefore R will be C. So then this equation becomes sigma minus sigma into B square divided by epsilon 0 into C, minus sigma into B square divided by epsilon 0 into C. So potential on the surface of C due to charge density on B can be written as minus sigma B square divided by epsilon 0 C. This is according to this equation. Plus potential on the surface of C due to charge density on A can be written as sigma into radius of A square divided by epsilon 0 into distance between the center to the surface of C, that will be small c. So sigma c by epsilon 0 plus sigma by epsilon 0 c can be taken out from these two, and what remains is A square minus B square, put as equation number 2. So it is given potential of A, total potential of A is equal to total potential of C. Therefore let us equate 1 and 2 together. So I will be getting sigma by epsilon 0 into A minus B plus sigma C by epsilon 0, that is equation number 1, total potential of A, that will be equal to total potential of C, sigma C by epsilon 0 plus sigma by epsilon 0 C into A square minus B square. So sigma by epsilon 0, sigma C by epsilon 0 can be cancelled. What remains is sigma by epsilon 0 into A minus B is equal to sigma by epsilon 0 in sigma by epsilon 0 C into A square minus B square can be written as A minus B into A plus B. So sigma by epsilon 0 into A minus B, sigma by epsilon 0 into A minus B can be cancelled. So 1 is equal to A plus B divided by C, and therefore the result will be A plus B is equal to C. A plus B is equal to C. The radius of the smaller sphere plus radius of the intermediate sphere is equal to radius of the bigger sphere.